In 1865, a French novelist named Jules Verne published a book called From the Earth to the Moon. In it, 3 adventurers are shot toward the moon inside a giant bullet fired from an enormous cannon buried in the Florida soil. While the story was pure fiction, Verne obsessed over the technical details. He calculated trajectories, estimated fuel requirements, and even placed his fictional launch site near Cape Canaveral, roughly 100 miles from where NASA would eventually build the Kennedy Space Center a century later. But Verne didn't stop at just visiting the moon. In his follow-up novel, he described elaborate plans for lunar colonies, complete with detailed discussions of how humans might survive in the airless void. He was wrong about almost everything, of course. You can't shoot people to the moon in a cannon without turning them into a fine red mist. But what matters is that Verne made people believe it was possible. He made them want it. For more than a century and a half, humanity has been planning to leave Earth. Not just to visit other worlds, but to stay there. To build cities on the moon, terraform Mars, and construct massive orbital habitats housing millions of people. These weren't just fantasies dreamed up by science fiction authors, though they certainly started there. No, these were detailed engineering proposals, complete with blueprints, cost estimates, and congressional testimonies. Plans drafted by Nazi rocket scientists, Soviet engineers, and American astronauts. Projects that received billions of dollars in funding before being unceremoniously canceled. This is the complete history of every serious attempt to colonize the solar system. Every rotating space station, every lunar outpost, every Martian city that was supposed to be built by the year 2000. We're going to examine why almost all of them failed, which ones might still happen, and whether we're destined to remain trapped on this planet forever, staring up at colonies we'll never build. Let's start at the beginning with the dreamers who made it all seem possible. Jules Verne wasn't alone in imagining humanity's future among the stars. In Russia, a school teacher named Konstantin Tsiolkovsky was conducting his own thought experiments. Between 1895 and the 1920s, Tsiolkovsky published a series of papers and books that laid the theoretical groundwork for spaceflight. But he didn't stop at getting into orbit. Tsiolkovsky envisioned enormous orbital colonies, which he called ether settlements, that would house thousands of people. He described these habitats in remarkable detail for someone writing decades before the first satellite. They would be massive cylinders, rotating to create artificial gravity through centrifugal force. Sunlight would be channeled inside using mirrors. Entire ecosystems would be enclosed within metal and glass. He wrote about space greenhouses growing food, closed-loop life support systems recycling air and water, and the social structures these orbital civilizations might adopt. In his 1920 essay, Dreams of Earth and Sky, Tsiolkovsky predicted that humanity would eventually abandon Earth entirely, spreading throughout the solar system in mobile space colonies. He even calculated the rotational speeds needed to simulate Earth gravity, the structural requirements for pressure vessels of different sizes, and the energy budgets required to sustain thousands of people in the void. None of this was idle speculation. Tsiolkovsky was solving real engineering problems for colonies that wouldn't be seriously considered for another 50 years. Around the same time, in Germany, a physicist named Hermann Oberth was working on similar concepts. His 1923 book, The Rocket into Planetary Space, wasn't just about getting to other planets, but staying there. Oberth proposed a rotating space station that would serve as a way station for lunar and Martian expeditions. His design was a wheel, about 30 meters in diameter, spinning to create artificial gravity. It would be assembled in orbit from components launched on multiple rockets, housing a crew of 10 in a pressurized rim. Oberth even specified the construction materials, favoring thin steel walls with meteorite shielding. He calculated that his station could be built for about 5 million Reichsmarks, which even then was recognized as hilariously optimistic. But here's what's important about these early visionaries. They were all self-taught. Verne was a novelist. Tsiolkovsky was a schoolteacher who was nearly deaf. Oberth was a physicist who couldn't get his doctoral thesis accepted because his professors thought spaceflight was impossible. Yet these men, working in isolation with nothing but mathematics and imagination, created the blueprints that would guide actual engineers decades later. When Werner von Braun began designing rockets for Nazi Germany, he cited Oberth as his inspiration. When NASA started planning space stations in the 1960s, they dusted off Tsiolkovsky's rotating cylinder concepts. The line from science fiction to science fact was direct and undeniable. But if we're being honest, all of these early concepts shared a fatal flaw. They assumed spaceflight would be easy. Verne thought you could just build a big enough cannon. Tsiolkovsky envisioned rockets the size of skyscrapers, but never grappled with the metallurgical challenges of building them. Oberth costed his space station at 5 million marks, when the actual figure would be closer to 5 billion. They were dreamers, and dreamers rarely worry about budgets. That would change in the 1950s when the dreamers started working for governments with actual money to spend. In 1952, Collier's magazine published a series of articles that would define space colonization imagery for the next 2 decades. The author was Werner von Braun, the former Nazi scientist who had designed the V-2 rocket and was now working for the United States Army. Von Braun had spent years refining his vision for human expansion into space, and Collier's gave him a mainstream platform to share it. The illustrations, painted by Chesley Bonestell and Fred Freeman, were so vivid and detailed that readers assumed they were depicting real plans rather than proposals. The centerpiece was a rotating wheel space station, 76 meters in diameter, housing a crew of 80. Unlike the vague concepts of earlier dreamers, von Braun specified everything. The station would be built from prefabricated sections launched on reusable rockets. Construction would take 5 years and require 364 rocket launches. The wheel would rotate at 3 revolutions per minute, creating 2/3 Earth gravity in the outer rim. The hub would remain stationary, serving as a docking port for arriving spacecraft. Power would come from solar concentrators, and the entire structure would be shielded from radiation and meteorites by a layered shell. Von Braun even detailed the crew composition: scientists, engineers, military personnel, and support staff. He described their daily routines, the food they'd eat, grown in hydroponic gardens, and the psychological challenges of long-duration spaceflight. This wasn't science fiction. This was an engineering proposal that happened to be published in a popular magazine. But the space station was just the beginning. Von Braun's Collier's series went on to describe a lunar base and a crewed mission to Mars. The moon base would be established using a fleet of spacecraft launched from the orbital station. He proposed a modular design with inflatable habitats buried under lunar regolith for radiation protection. A crew of 12 would establish the first outpost near the lunar South Pole, where crater shadows might harbor water ice. They would remain for 6 weeks, conducting geological surveys and testing equipment. Future expeditions would expand the base, eventually supporting a permanent crew of 50. The timeline? Von Braun suggested the space station could be operational by 1963, the lunar base by 1965. These dates weren't random speculation. He'd done the math, accounting for rocket production rates, orbital construction time, and mission planning. Of course, he'd made one critical miscalculation. He assumed the United States government would actually fund it. The entire program, he estimated, would cost about $4 billion spread over a decade. That's roughly $45 billion in today's money. Expensive, certainly, but achievable for a superpower in a space race. Congress took one look at the price tag and laughed him out of the room. But here's where things get interesting. While politicians dismissed von Braun's plans as too expensive, the public loved them. The Collier's articles were a sensation, reprinted in multiple languages and discussed in newspapers worldwide. Walt Disney saw the potential for entertainment and partnered with von Braun to produce a series of television specials. Man in Space, Man and the Moon, and Mars and Beyond aired in 1955 and 1957, reaching audiences of tens of millions. Disney's animators brought von Braun's technical drawings to life with full-color animations of rotating space stations and lunar bases. For the first time, average people could visualize what living in space might actually look like. This wasn't Flash Gordon pulp fantasy with rocket ships shaped like bullets and spacemen in fishbowl helmets. This looked real, plausible, inevitable. Von Braun appeared on screen in a suit and tie, speaking calmly about orbital mechanics and launch windows as if discussing something as mundane as bridge construction. The effect was profound. An entire generation of children grew up believing they'd live to see cities in space. Engineering students chose aerospace careers because of those Disney programs. When President Kennedy announced the Apollo program in 1961, he was tapping into a cultural momentum that von Braun and Disney had created. Yet, for all the public enthusiasm, von Braun's grand vision never materialized. NASA was established in 1958, and von Braun became director of the Marshall Space Flight Center, where he oversaw development of the Saturn V rocket. But instead of building his rotating space station, NASA focused on a narrow goal: beating the Soviets to the moon with a basic landing and return mission. No permanent base. No rotating station. Just flags and footprints. Von Braun publicly supported Apollo, but privately he was frustrated. He'd designed the Saturn V to be capable of launching station components and lunar base equipment. The rocket could lift 140 tons to low Earth orbit, enough to build a space station with just a few launches. But NASA's leadership, particularly Administrator James Webb, saw Apollo as a political weapon, not a stepping stone to colonization. Get to the moon first, prove American superiority, declare victory, and move on. Von Braun's grand plans were filed away as future possibilities. We're still waiting. While von Braun was selling his vision to American audiences through magazines and television, the Soviet Union was developing their own colonization plans in complete secrecy. We only learned the full extent of these proposals decades later, when aging engineers began publishing memoirs, and classified documents were gradually declassified after the Soviet collapse. What we now know is staggering. The Soviets weren't just planning to visit the moon. They intended to colonize it, militarize it, and use it as a staging ground for Mars missions. The program was called Zvezda, meaning star, and it was far more ambitious than anything NASA was considering during the same period. The Zvezda lunar base design emerged from the OKB-1 Design Bureau under Sergei Korolev in the early 1960s. Korolev, the chief architect of the Soviet space program, envisioned a permanent outpost supporting up to 12 cosmonauts for extended stays of up to 1 year. Unlike von Braun's proposals, which assumed gradual build-up over many missions, Zvezda would be delivered in large prefabricated sections. The base would consist of 4 main modules: habitation, laboratory, power generation, and life support. Each module would be roughly cylindrical, about 10 meters long and 4 meters in diameter, transported to the lunar surface aboard heavy landers. The modules would be connected by flexible tunnels and partially buried under regolith, using remotely operated bulldozers to provide radiation shielding. Power would come from a small nuclear reactor, not solar panels, giving the base consistent energy even during the 2-week lunar night. Korolev's team calculated that Zvezda could support continuous habitation for 5 years before requiring major resupply or component replacement. The timeline called for robotic precursor missions in 1967, first crewed landing in 1968, and base operational by 1970. To support Zvezda, Korolev designed the ELEK lunar expedition craft, the Soviet equivalent of the Apollo lunar module. But where the LM was a lightweight craft designed to land 2 men for a few days, the LEK was built for heavy cargo delivery and crew rotations to a permanent base. It could carry 4 cosmonauts or 3 cosmonauts plus 2,000 kilograms of supplies. The design featured a reusable ascent stage, which could be refueled on the lunar surface using propellant delivered by robotic cargo landers. This would allow the same LEK to make multiple trips between lunar orbit and the surface, dramatically reducing the cost per mission compared to Apollo's expendable architecture. Soviet engineers calculated that with orbital refueling and surface reuse, they could sustain lunar base operations for 1/10 the cost of equivalent Apollo-style missions. It was genuinely innovative engineering, decades ahead of the reusable concepts that SpaceX would later pioneer. But there was another, darker aspect to Soviet lunar plans. The Zvezda base wasn't purely scientific. Classified documents revealed plans for military applications: reconnaissance of Earth, testing weapons in lunar gravity, and establishing territorial claims. Vladimir Chalome, a rival to Korolev who led the OKB-52 Design Bureau, pushed even more aggressive militarization. His competing proposal, the Almaz lunar base, would be explicitly military in nature, housing weapons to destroy American satellites and potentially target terrestrial installations. Chalome envisioned a crew of 8 military cosmonauts operating surveillance equipment and, if necessary, weapons systems. The proposal included designs for lunar-launched interceptor rockets and surface-to-orbit cannons. This sounds insane until you remember this was the height of the Cold War, when both superpowers were genuinely paranoid about the other weaponizing space. The United States had its own classified studies on lunar military bases, though none got as far as the Soviet proposals. All of these grand Soviet plans depended on one critical piece of hardware: the N-1 rocket. This was the Soviet answer to the Saturn V, a massive booster capable of lifting 95 tons to low Earth orbit. The N-1 would launch the LEK, the Zvezda modules, and everything else needed for lunar colonization. Without it, none of these plans were possible. Between 1969 and 1972, the Soviets attempted 4 N-1 launches. All 4 exploded. The first test, in February 1969, lasted 70 seconds before an engine failure caused the rocket to crash. The second attempt, in July 1969, just days before Apollo 11 landed on the Moon, was catastrophic. The N-1 lifted off, immediately lost control, fell back onto the launch pad, and exploded with a force equivalent to 7,000 tons of TNT. It remains one of the largest non-nuclear explosions in human history. The third and fourth tests in 1971 and 1972 failed at higher altitudes, but still ended in fireballs. After the fourth failure, the Soviet leadership quietly canceled the program. Korolev had died in 1966, taking much of the institutional knowledge with him. His successors couldn't solve the N-1's fundamental design flaws. Too many engines, 30 in the first stage alone, with no realistic way to test them all together before launch. By 1974, the N-1 program was officially terminated. The remaining rockets were scrapped, and Zvezda base plans were filed away as historical curiosities. Today, you can visit the Baikonur Cosmodrome in Kazakhstan and see the massive concrete launch pad where the second N-1 exploded. The blast crater has been filled in, but the scorched ground is still there, a monument to the grandest lunar colonization plan that never happened. Recently declassified documents suggest that if just one N-1 had successfully reached orbit, political pressure would have forced continued funding. The Soviets might have established their lunar base by the mid-1970s, fundamentally altering the trajectory of human space exploration. Instead, after Apollo 17 in 1972, no human has ventured beyond low Earth orbit. Both superpowers had the plans, the technology, and briefly the funding to colonize the Moon. Both chose to stop. But here's the thing. NASA didn't immediately give up on lunar colonization after Apollo 11. In fact, the agency had detailed plans to transition from short Apollo visits to permanent habitation. The program was called Apollo Applications, and it represented NASA's attempt to leverage the expensive Apollo infrastructure for long-term exploration. Between 1965 and 1972, NASA engineers developed concepts for extended lunar module stays, surface habitats, and semi-permanent bases. These weren't vague proposals. They had part numbers, contractor agreements, and line items in congressional budgets. For a brief moment, lunar colonization was actually happening. The Apollo Applications program began in 1965, before the first Apollo mission had even flown. NASA's leadership recognized that the massive investment in Apollo technology, the Saturn V rocket, the command module, the lunar module, would be wasted if used only for brief flag-planting missions. The logical next step was to extend mission durations and build up surface infrastructure. The first phase called for modified lunar modules capable of supporting 2 astronauts for 2 weeks instead of 2 days. Engineers at Grumman, the LM contractor, designed extended LM variants with enlarged descent stages, carrying extra oxygen, water, food, and battery power. These LM shelter configurations would land near previous Apollo sites, allowing astronauts to conduct extensive geological surveys and equipment tests. NASA planned to fly these extended missions as Apollos 18, 19, and 20, following the initial landing successes. But the real ambition came with the second phase, the Lunar Surface Base. This concept emerged from studies conducted at NASA's Marshall Space Flight Center and the Langley Research Center between 1968 and 1970. The base would be established using modified Saturn V launches carrying specialized payload, a habitat module, power systems, life support equipment, and a pressurized rover. The habitat module was essentially a horizontal cylinder, 10 meters long and 4.5 meters in diameter, with enough volume for 4 astronauts to live for 90 days. It would be delivered to the lunar surface on a modified LM descent stage. Then astronauts rather, would bury it under lunar soil using a small bulldozer blade attached to a rover. The habitat interior was divided into crew quarters, laboratory space, a galley, and exercise area. Engineers designed fold-out bunks, a small shower using recycled water, and even a centrifuge for medical monitoring. Power would come from a radioisotope thermoelectric generator, the same technology used on deep space probes, providing steady electricity regardless of day-night cycles. The pressurized rover, called the Lunar Exploration Rover, would allow 2 astronauts to venture hundreds of kilometers from base, conducting week-long traverses across the lunar highlands. NASA presented this plan to Congress in 1969, requesting funding to begin hardware development. The estimated cost was $2.6 billion to establish the first base by 1976, with annual operating costs of $500 million. Nixon's administration looked at those numbers and immediately started cutting. The problem wasn't technical feasibility. NASA had solved the engineering challenges. The problem was political will. The space race was over. America had won. Kennedy's goal of landing a man on the moon before the Soviets had been achieved. Continuing to spend billions on lunar bases served no obvious strategic purpose. The Vietnam War was consuming the federal budget. Domestic programs needed funding. Space exploration was no longer a priority. In 1970, NASA was informed that Apollos 18, 19, and 20 were canceled. The hardware for these missions had already been built. 3 complete sets of Saturn V rockets, command modules, and lunar modules were sitting in warehouses, ready to fly. Instead, they became museum exhibits. You can visit them today. The Saturn V displayed outside the Johnson Space Center in Houston is the rocket that would have launched Apollo 18. The lunar module at the Cradle of Aviation Museum in New York was destined for Apollo 19. They never flew. The astronauts assigned to these missions, including geologist Harrison Schmitt, who would have conducted the most scientifically valuable lunar traverses, were reassigned or retired. Schmitt did eventually reach the moon on Apollo 17, the final mission, but it was a brief 3-day visit instead of the 90-day base deployment he'd been training for. What's frustrating is how close NASA came to transitioning to permanent lunar presence. The technology was ready. The astronauts were trained. The rockets were built. All that was missing was continued funding, and that evaporated the moment the political objective was achieved. This pattern, ambitious plan, initial funding, technical success, then cancellation due to cost, would repeat itself again and again over the next 50 years. But we're getting ahead of ourselves. Before we leave the 1960s, we need to talk about Mars, because while the moon was the immediate goal, Mars was always the dream. And no one dreamed bigger than Wernher von Braun. In 1948, years before his Collier's Magazine articles, von Braun wrote a technical manuscript called Das Mars Projekt, the Mars Project. It was finally published in 1952, and it remains one of the most detailed Mars mission proposals ever conceived. Von Braun wasn't interested in a simple flyby or a flags and footprints landing. He was planning full-scale colonization from day one. The Mars Project called for a fleet of 10 spacecraft carrying 70 crew members. Yes, 70. Von Braun believed the first Mars mission needed to be large enough to establish a permanent base immediately, rather than risk a small crew dying if anything went wrong. The spacecraft would be assembled in Earth orbit at his rotating space station, then launched toward Mars in a single convoy. 7 ships would be passenger vessels, each carrying 10 crew in rotating sections to provide artificial gravity during the 7-month journey. 3 ships would be cargo vessels, carrying the equipment needed to establish a base. Habitat modules, rovers, power generators, and supplies for 2 years. Once in Mars orbit, the fleet would deploy 3 landing craft. Here's where von Braun's plan gets weird. He assumed Mars had a thick atmosphere, based on telescopic observations available in the 1940s. So, his landers were winged gliders that would aerobrake through the Martian atmosphere and land on skids, like the space shuttle. The first lander would touch down, and its crew would spend several weeks constructing a landing strip using bulldozers carried in the cargo. Then the other 2 landers would arrive, gliding onto the prepared runway like airplanes. It sounds absurd now, but remember, in 1948, nobody knew what Mars was actually like. The best telescopes showed polar ice caps and seasonal color changes that suggested vegetation. A thick atmosphere seemed plausible. Once on the surface, the 70-person crew would establish a base using prefabricated modules. Von Braun designed these as a series of connected cylinders forming a cross shape when viewed from above, similar to a small village. The central hub would contain life support and power systems, with wings radiating out for habitation, laboratories, workshops, and storage. The crew would spend 15 months on Mars, waiting for the planets to realign for the return journey, conducting geological surveys and searching for life. Then they'd take off, rendezvous with the orbiting passenger ships, and return to Earth. Total mission duration: nearly 3 years. Von Braun calculated the entire project would require 950 rocket launches to deliver all the components to Earth orbit for assembly. Even using his optimistic cost estimates, the total price tag would exceed $100 billion in today's money. When he presented this plan to potential backers in the 1950s, they thought he was joking. But here's what's remarkable. Setting aside the wrong assumptions about Mars's atmosphere and the absurd cost, much of von Braun's engineering was sound. The orbital assembly concept, using artificial gravity for crew health, carrying redundant systems, these are all principles that current Mars mission plans incorporate. Von Braun understood that Mars colonization couldn't be done on the cheap. You either commit to a large, expensive, robust mission with a real chance of success, or you don't go at all. This philosophy would be mostly forgotten in later decades, as NASA tried repeatedly to design cut-rate Mars missions that never got funded because they were too risky. Von Braun's Mars project was never seriously considered for actual implementation, but it established a template. Mars colonization is possible, but only if you're willing to spend truly staggering amounts of money. Governments looked at that equation and decided they weren't willing. At least, not yet. So, as the 1960s ended, humanity had detailed plans to colonize the Moon and Mars, the technology to begin implementation, and absolutely no intention of following through. The dreamers had done their job. They'd proven it was possible. They'd inspired a generation. But inspiration doesn't build space stations, and dreams don't pay for rocket fuel. The next phase would require something the dreamers rarely possessed: political pragmatism and a willingness to compromise. That's where things would get really complicated. In 1974, a Princeton physics professor named Gerard K. O'Neill published a paper that would fundamentally change how people thought about space colonization. The paper was titled "The Colonization of Space," and its central premise was radical. Forget about colonizing planets. Instead, build artificial worlds in orbit where humans could control every environmental parameter. No thin atmospheres, no toxic soil, no punishing gravity wells. Just massive rotating cylinders in space, housing millions of people in shirt-sleeve comfort with artificial gravity, Earth-like weather, and carefully designed ecosystems. O'Neill wasn't proposing this as distant science fiction. He had his undergraduate students run the numbers, and the math worked. These space colonies could be built with existing technology and materials mined from the moon. More importantly, O'Neill argued they could be economically self-sustaining within a few decades, paying for themselves by beaming solar power back to Earth. This wasn't a dream. This was engineering. O'Neill's paper caught the attention of Stuart Brand, the publisher of the Whole Earth catalog, who helped popularize the concept through articles and lectures. By 1975, O'Neill had refined his ideas into a complete architectural vision with 3 progressively larger designs. Island 1 would be the prototype, a modest cylinder just 500 meters long and 200 meters in diameter, housing 10,000 people. It would rotate once per minute to generate artificial gravity through centrifugal force. The interior would be divided into 3 lengthwise strips. 2 would be transparent windows allowing sunlight in, while the third would be land for agriculture and habitation. Mirrors outside the cylinder would redirect sunlight through the windows during the colony's artificial day, then tilt away to create night. The cylinder's rotation would keep everything pressed against the inner surface, creating a curved landscape where you could literally see your neighbors' houses overhead on the opposite side. Island 1 would be constructed from lunar materials, specifically aluminum and titanium extracted from regolith, launched into space using electromagnetic mass drivers. O'Neill calculated that Island 1 could be built for about $200 billion spread over 15 years, which in 1975 money seemed achievable for a consortium of wealthy nations or even private industry. But Island 1 was just the beginning. Island 2 would be twice as large, 800 meters long and 600 meters in diameter, housing 140,000 people. Island 3, the full realization of O'Neill's vision, would be absolutely massive. 2 counter-rotating cylinders, each 32 kilometers long and 6.5 kilometers in diameter, housing a total of several million people. Each cylinder would have 6 lengthwise strips alternating between transparent windows and land, creating 3 valleys with agricultural zones, urban centers, and wilderness preserves. The interior would be landscaped to resemble terrestrial environments, complete with rivers, forests, and artificial clouds created by precisely controlled humidity. O'Neill envisioned different cylinders specializing in different climates. One might recreate the Pacific Northwest with redwood forests and rainy weather, while another would simulate the Mediterranean with olive groves and sunny skies. Residents could travel between cylinders using transit tubes at the rotation axis, experiencing brief moments of weightlessness before entering another world. The scale was staggering. A single Island 3 cylinder would have more interior land area than Bermuda and could theoretically house 10 million people if densely populated. O'Neill calculated that materials from the moon could supply enough raw material for hundreds of such colonies, eventually housing billions of people throughout the solar system. O'Neill's ideas exploded into popular consciousness with his 1976 book, The High Frontier: Human Colonies in Space. The book became a bestseller, translated into multiple languages, and inspired a grassroots movement unlike anything space exploration had seen before. Thousands of enthusiasts formed the L5 Society, named after Lagrange Point 5, one of the gravitationally stable locations where O'Neill proposed building his colonies. The L5 Society wasn't a fan club. These were engineers, scientists, and activists who genuinely believed they would live in space colonies within their lifetimes. The society grew to over 10,000 members by 1980, lobbying Congress for funding, organizing technical conferences, and publishing detailed newsletters about colony construction methods. They commissioned artists like Don Davis and Rick Guidis to create photorealistic paintings of O'Neill's cylinders, showing lush landscapes curving overhead, rivers flowing upward along the cylinder walls, and cities nestled in valleys that shouldn't exist. These paintings were so convincing that many people assumed they depicted actual plans rather than proposals. NASA took notice and funded 2 summer studies in 1975 and 1977 at Stanford University and NASA Ames Research Center, bringing together engineers, architects, and scientists to evaluate O'Neill's concepts. The Stanford torus emerged from these studies as an alternative to O'Neill's cylinders. The torus was essentially a giant donut, 1,800 meters in diameter, rotating once per minute. The interior of the tube would provide living space for 10,000 people, with the outer wall being the floor due to rotation. The center of the donut would house a zero-gravity industrial zone and docking facilities, connected to the rotating torus by spokes. The advantage of the torus design was structural simplicity. A circular cross-section is easier to pressurize than O'Neill's cylindrical strips with their alternating windows and land sections. The Stanford torus study produced incredibly detailed specifications, down to the types of crops that would be grown, the layout of residential modules, and even the social dynamics of an isolated population. The study concluded that a torus could be constructed for about $190 billion in 1975 money, assuming lunar mining operations were already established. NASA published a lavishly illustrated report that looked more like an architectural magazine than an engineering document, complete with cutaway views showing shopping areas, parks, and housing complexes inside the rotating donut. Another variant was the Bernal sphere, actually one of the older concepts dating back to 1929, but revisited during the O'Neill era. The Bernal sphere was exactly what it sounds like, a giant hollow ball, about 16 kilometers in circumference, rotating to provide gravity on its inner surface. The sphere would be divided into zones, with habitation and agriculture on the equatorial regions where rotation provided the strongest artificial gravity, and low-gravity industrial areas near the poles. The sphere design had advantages in terms of structural efficiency, as a sphere distributes pressure evenly, but it was more difficult to construct than cylinders or toruses. Still, studies suggested it could house 20,000 to 30,000 people with appropriate interior landscaping. All of these designs, the O'Neill cylinders, the Stanford torus, the Bernal sphere, shared common infrastructure requirements. They needed massive amounts of material, preferably from the moon to avoid the expense of launching from Earth's gravity well. They needed energy, which would come from enormous solar panel arrays. They needed closed-loop life support systems that could recycle air, water, and waste with near-perfect efficiency. And they needed artificial ecosystems that could remain stable for decades without external inputs. Here's where the optimism of the 1970s becomes almost painful in retrospect. O'Neill and the L5 Society genuinely believed that space colonies would be economically viable because they could export solar power to Earth. The concept was called space solar power. Colonies would manufacture enormous solar panel arrays, collect energy 24 hours a day without atmospheric interference, and beam it to Earth using microwave transmitters. Receiving stations on Earth would convert the microwaves back into electricity and feed it into the grid. O'Neill calculated that space-based solar power could provide unlimited clean energy at competitive prices, making space colonies not just self-sustaining, but profitable. The L5 Society lobbied heavily for government investment in this technology, arguing that space colonization should be understood as an energy infrastructure project, not just an exploration program. For a brief moment in the late 1970s, this idea had traction. The energy crisis following the 1973 oil embargo had made alternative energy a national priority. Space solar power seemed like a long-term solution that would also drive space colonization. NASA conducted feasibility studies. Congressional hearings were held. The Department of Energy evaluated whether beaming gigawatts of microwave energy through the atmosphere was safe. Spoiler: they concluded it probably was, as long as you kept people away from the receiving stations. But then reality intruded. The economic analysis for space solar power kept getting worse as engineers looked closer at the details. The receiving stations on Earth would need to be enormous, several kilometers across, and would require huge land areas kept clear of people and animals due to microwave exposure. The transmission efficiency was lower than initially hoped, meaning you'd need even larger solar arrays in space to deliver competitive electricity prices. Most damaging, the cost estimates kept climbing. Early projections suggested space solar power could be cost-competitive with terrestrial power plants if launch costs dropped below $200 per kilogram. But launch costs in the late 1970s were over $10,000 per kilogram using the space shuttle, which was supposed to make spaceflight cheap. Even optimistic projections for reusable launch systems couldn't get costs low enough to make the economics work. By 1980, most serious analysis concluded that space solar power was technically feasible, but economically absurd. You could build nuclear power plants or cover deserts with terrestrial solar panels for a fraction of the cost. The business case for O'Neill colonies evaporated. Without a revenue stream, the colonies would be purely government-funded science projects, and governments weren't going to spend hundreds of billions on space habitats when they'd just canceled lunar bases for costing too much. The L5 Society continued advocating through the 1980s, but momentum bled away as it became clear that no space colony would be built by 2000 or 2020, or possibly ever. The Society eventually merged with the National Space Society in 1987. And while the combined organization still promotes space settlement, the fervent belief that it would happen soon died in the 1980s. Looking back, what's striking about the O'Neill colony movement is how thoroughly the engineering was developed. These weren't vague concepts. NASA had detailed CAD drawings, materials lists, construction sequences, and cost breakdowns. The technology was available. What was missing was the political will to spend the money and the economic justification for doing so. This would become a recurring theme. Space colonization keeps being canceled, not because it's impossible, but because it's expensive and no one can articulate why it's worth the cost. By the 1980s, NASA had a new flagship program, the Space Shuttle. The shuttle was supposed to make spaceflight routine and affordable, launching every week and cutting costs to a fraction of expendable rockets. With that capability, the agency believed it could finally return to the Moon and establish a permanent base. The shuttle could launch base components, construction crews, and supplies on regular flights. Starting in 1984, NASA commissioned multiple studies for shuttle-based lunar architectures, and for a few years, it looked like lunar colonization might actually happen. The most comprehensive proposal came from astronaut Sally Ride's 1987 report, often called the Ride Report, which outlined 4 possible futures for NASA: a mission to Mars, a return to the Moon with a permanent base, a mission to a near-Earth asteroid, or development of a space station. The lunar base option envisioned a modular outpost at the lunar South Pole, established using shuttle-launched components assembled in low Earth orbit before being sent to the Moon. The Ride report's lunar base design was surprisingly practical compared to earlier proposals. It would start small, with just 4 astronauts staying for 30 days at a time, gradually expanding to a crew of 12, staying for 6 months or longer. The base would consist of interconnected inflatable modules, a technology that was being developed by companies like ILC Dover, the same contractor that made Apollo spacesuits. Inflatable habitats had several advantages. They packed efficiently for launch, could be enlarged to provide ample living space once deployed, and their flexible walls could be covered with lunar regolith for radiation protection. The Ride report proposed launching habitat modules on the shuttle, transferring them to a lunar transfer vehicle in orbit, landing them on the Moon using a reusable lander, and then inflating them on the surface. Astronauts would bury the habitats under several meters of regolith using robotic bulldozers, creating radiation-shielded volumes comparable to underground bunkers. Power would come from nuclear reactors or large solar panel arrays depending on the landing site. The base would focus on science, testing in situ resource utilization, extracting oxygen from lunar regolith, and potentially mining water ice from permanently shadowed craters. The Ride report estimated this base could be operational by the late 1990s, with sustained funding of about $3 billion per year. Another proposal from this era was First Lunar Outpost, developed by NASA's Office of Exploration in the late 1980s. First Lunar Outpost was even more minimalist than the Ride report concept, focusing on short-term visits using upgraded Apollo-style hardware. The idea was to land 2 astronauts for 7 to 14 days, conduct intensive scientific exploration, and return, repeating these missions several times per year. Over time, the missions would leave behind equipment that would gradually accumulate into a semi-permanent base. Habitats, rovers, power systems, and scientific instruments would remain on the surface between crew visits, and eventually there would be enough infrastructure to support longer stays. This incremental approach was supposed to be more affordable than building a complete base up front, spreading costs over many years. First Lunar Outpost had serious engineering work behind it. NASA contractors developed detailed designs for a lunar lander that could be launched on existing rockets, a small pressurized rover based on Apollo lunar roving vehicle technology, and compact habitat modules that could be connected together like Lego bricks. The total cost for the first decade of operations was estimated at about $30 billion, which seemed reasonable compared to Apollo's $150 billion price tag. But here's where things went wrong. In 1989, President George H.W. Bush announced the Space Exploration Initiative, a grand vision to return to the Moon and send humans to Mars. Bush gave a speech on the 20th anniversary of Apollo 11, standing on the steps of the National Air and Space Museum, declaring that America would establish a lunar base and then journey to Mars. It sounded like Kennedy's Rice University speech, an inspiring call to action backed by presidential authority. NASA was directed to develop a detailed plan, and the agency delivered the 90-day report in November 1989. This report would become infamous as one of the most tone-deaf proposals in NASA history. Instead of building on the relatively affordable concepts from the Ride report or First Lunar Outpost, the 90-day report proposed a massive Apollo-style program requiring a new heavy-lift rocket, a new space station, new lunar landers, and new Mars spacecraft. The cost estimate, $450 billion over 20 to 30 years. Congress took one look at that number and declared the entire initiative dead on arrival. The Space Exploration Initiative was quietly abandoned by 1993, and with it went the last serious attempt to establish a lunar base in the 20th century. The frustrating thing is that critics at the time, including many within NASA, pointed out that the 90-day report was unnecessarily expensive. You didn't need a new space station. You didn't need a new heavy-lift rocket. The shuttle-derived launchers would work. You didn't need to build everything before starting. The incremental approach of first lunar outpost could have been implemented for a fraction of the cost. But NASA's institutional culture had been shaped by Apollo, which succeeded through brute force spending and crash development. The agency didn't know how to do space exploration cheaply. Every proposal defaulted to building new infrastructure from scratch, hiring thousands of contractors, and spending decades on development. This approach worked once, during the Cold War space race when budgets were essentially unlimited. It hasn't worked since, and it's why nearly every post-Apollo colonization plan has been canceled. NASA kept designing Cadillacs when Congress wanted Toyotas, and eventually, Congress just stopped buying. While NASA was fumbling lunar base plans, a grassroots movement was forming around Mars. It started in 1981 when a young engineer named Robert Zubrin attended a conference called The Case for Mars, organized by space enthusiasts frustrated with NASA's lack of ambition. The conference brought together scientists, engineers, and advocates who believed Mars should be humanity's next destination, not the Moon. They argued that Mars had water, a thin but useful atmosphere, and the potential for long-term self-sufficiency in ways the Moon never could. The Case for Mars conferences became annual events through the 1980s, attracting hundreds of attendees and producing volumes of technical papers on Mars mission architectures, life support systems, and in situ resource utilization. This was the Mars Underground, not an official organization but a loose network of people determined to make Mars colonization happen regardless of NASA's priorities. Robert Zubrin emerged as the movement's most eloquent advocate. In the mid-1980s, he began developing what would eventually become Mars Direct, a mission architecture that would revolutionize Mars planning, but we'll get to that in the next section. During the 1980s, Zubrin and others were laying the groundwork, arguing that Mars missions didn't need to cost hundreds of billions. They could be done for tens of billions if you used in situ resources, made propellant on Mars instead of carrying it from Earth, lived off the land instead of bringing everything with you, and accepted higher risks instead of over-engineering everything. These ideas were heretical to NASA's safety culture, but appealing to anyone who'd watched decades of overpriced proposals die in Congress. The Soviet Union, meanwhile, was developing its own Mars plans using its new Energia heavy-lift rocket. Energia was comparable to the Saturn V in capability, able to lift 100 tons to low Earth orbit, and Soviet engineers designed a Mars expedition architecture around it. The plan called for assembling a Mars spacecraft in orbit using multiple Energia launches, with a crew of 6 making a 2-year round-trip mission. The spacecraft would use nuclear electric propulsion for efficient transit, and the lander would be a massive vehicle capable of landing significant cargo and crew. The Soviets planned to launch this mission in the early 2000s, establishing a small base during the initial landing and expanding it on subsequent missions. The program was named Mars 5M and had serious engineering development underway by the late 1980s. But then the Soviet Union collapsed in 1991, and with it went the funding for Mars 5M. The Energia rocket flew twice, successfully both times, then was canceled due to lack of money. The partially constructed Mars spacecraft components were scrapped or left to rust in warehouses. Some of that hardware still exists today, sitting in Russian museums, monuments to a Mars program that came tantalizingly close to reality before geopolitics intervened. Back in the United States, multiple lunar base studies were conducted through the 1980s with names like Lunex and Horizon, although Horizon actually dated back to 1959 as a U.S. Army proposal. These studies all shared common elements: bases at the lunar poles where permanently shadowed craters might hold water ice, habitats buried under regolith for radiation protection, and in situ resource utilization to reduce dependence on Earth supplies. The in situ resource utilization concept was particularly important. Engineers had figured out that lunar regolith could be heated to extract oxygen, which makes up about 40% of the soil by mass. That oxygen could be used for breathing, and when combined with hydrogen brought from Earth, turned into water. Even better, oxygen is also a rocket propellant. If you could manufacture oxygen on the Moon, you could refuel spacecraft there instead of launching all propellant from Earth, dramatically reducing mission costs. This wasn't speculative. Lab experiments in the 1980s successfully extracted oxygen from simulated lunar soil. The technology worked. What didn't work was convincing anyone to fund a billion-dollar demonstration mission to prove it at lunar scale. All of these lunar base studies concluded the same thing: technically feasible, economically expensive, politically unlikely. No matter how you designed the base, whether you used inflatables or rigid modules, whether you mined ice or brought all supplies from Earth, whether you used the shuttle or a new rocket, the bottom line cost was always in the tens of billions of dollars. And every time NASA presented these plans to Congress, the response was the same. Why? What's the compelling reason to spend this money? Apollo had been justified by Cold War competition, but the Soviet Union was collapsing by the late 1980s. Scientific research could be done with robotic missions for 1/10 the cost. Mining resources on the Moon only made sense if you were building something in space that needed those resources, and we weren't. The lunar base proposals of the 1980s failed not because the engineering was flawed, but because no one could answer the why question with an explanation that justified the cost. Now, let's talk about Venus, because while everyone else was focused on the Moon and Mars, a few visionaries looked at the hottest planet in the solar system and thought, you know what, we could live there. This sounds insane until you learn about the discoveries Soviet Venera probes made in the 1970s. Venus's surface is a hellscape. 470 degrees Celsius, atmospheric pressure 90 times Earth's, and clouds of sulfuric acid. But about 50 kilometers up in the atmosphere, conditions are surprisingly pleasant. The temperature is around 25 degrees Celsius, the pressure is 1 atmosphere, and sunlight is abundant. If you could build a floating city at that altitude, humans could walk around in shirt sleeves, needing only air supply and protection from the sulfuric acid. Jeffrey Landis, a NASA scientist, developed detailed proposals for Venus cloud cities starting in the 1990s, building on Soviet studies from the 1970s. The concept works because breathable air, a mixture of nitrogen and oxygen, is a lifting gas in Venus's carbon dioxide atmosphere. A habitat filled with normal air would float at the right altitude without needing any active lift. You could build dirigible-style structures, essentially zeppelins the size of aircraft carriers, with pressurized crew compartments hanging below giant envelopes filled with breathable air. Solar panels on the upper surface would provide abundant power. The sulfuric acid cloud layer is actually below the habitation altitude in Landis's designs, so structures wouldn't be continuously bathed in acid, though you'd still need acid-resistant materials for any components that descended into the clouds. The real advantage of Venus over Mars is that it's closer to Earth, with shorter transit times and more frequent launch windows. The gravity is nearly Earth normal, preventing the bone loss and muscle atrophy that would plague Mars colonists. And the atmosphere provides protection from radiation that Mars's thin air can't offer. So why don't we hear more about Venus colonization? Several reasons. First, there's nowhere to land. If you want to visit the surface for mining or research, you're building machines that must survive conditions that melt lead. Second, there's no exit strategy. If something goes wrong on Mars, you can potentially wait on the surface for rescue. If your Venus Cloud City starts sinking, you've got minutes before you're cooked alive. Third, there's no pathway to self-sufficiency. Mars has water ice, minerals, and soil where you could grow food. Venus's atmosphere is missing nitrogen at useful concentrations, has no water, and offers no solid resources except whatever you can mine from the hellish surface. A Venus colony would be completely dependent on Earth for supplies forever. Still, Landis and others continue to advocate for Venus exploration, arguing that floating research stations could be established much more easily than Mars bases, and they're not wrong. The engineering challenges of a Venus Cloud City are actually less severe than a Mars surface base in many respects. It's just that nobody wants to live in a balloon 50 kilometers above a toxic hellscape when Mars offers the romantic vision of walking on another world. Finally, let's talk about asteroid colonies, because in the 1970s and 80s, many people believed the asteroid belt would be humanity's economic frontier. O'Neill's space colony concepts included plans for mining asteroids, using electromagnetic mass drivers to shoot raw materials to orbital factories where they'd be processed into colony construction materials. Asteroids offered several advantages. They're already in space, eliminating the need to launch materials from a gravity well. Many asteroids contain high concentrations of valuable metals like platinum, nickel, and cobalt. Some asteroids are essentially flying mountains of iron, perfect for manufacturing spacecraft and habitats. And asteroids don't have significant gravity, meaning you could land on one with minimal fuel, unlike planets or moons. The fantasy that emerged was of independent asteroid mining colonies, small settlements of a few hundred people living on hollowed-out asteroids, prospecting for valuable materials and shipping them back to Earth orbit for profit. This was the space cowboy fantasy, rough and tumble frontier outposts where individualists could strike it rich. Several studies in the 1980s tried to evaluate the economics, and the results were mixed. Yes, some asteroids contain trillions of dollars worth of platinum group metals, but the cost of mining them, refining them in space, and shipping them to Earth would be hundreds of billions of dollars in infrastructure development. You'd have to mine asteroids continuously for decades before turning a profit, assuming the market didn't crash once you flooded Earth with cheap platinum. And that's assuming you could solve the technical challenges. Building habitats on irregularly shaped tumbling rocks with no gravity, keeping them supplied with air and food across distances measured in hundreds of millions of kilometers, and preventing your workforce from going insane from isolation. Despite these challenges, Asteroid colony concepts remained popular through the 1980s because they seemed more achievable than planetary colonies. You didn't need massive rockets to land on an asteroid. You didn't need to terraform anything. Just hollow out a rock, spin it for gravity, and you've got a home. But as analysis continued, the problems multiplied. Most asteroids are loose rubble piles, not solid rock, making tunneling and construction extremely difficult. They have no resources for life support, so everything, air, water, food, would need to be imported. The radiation exposure is extreme without planetary magnetic fields or thick atmospheres for protection. And the social dynamics of small, isolated populations were increasingly understood to be problematic. Studies of Antarctic research stations and nuclear submarines suggested that fewer than a few dozen people living in confined spaces for extended periods leads to serious psychological problems. By the 1990s, asteroid colony enthusiasm had faded, though asteroid mining continued to be proposed as a robotic operation supporting orbital infrastructure, not a colonization destination. So, the 1970s and 80s produced a remarkable collection of detailed colony proposals, none of which were built. O'Neill cylinders, lunar bases, Mars expeditions, Venus cloud cities, and asteroid settlements all received serious engineering attention, generated beautiful artwork, and inspired thousands of people to careers in aerospace. But when it came time to actually fund construction, the answer was always no. The next section will cover the 1990s and 2000s, when mission planners finally started designing proposals that might, possibly, actually happen. Spoiler alert, most of them didn't. In the summer of 1990, an engineer named Robert Zubrin was working at Martin Marietta on yet another bloated Mars mission study when he had an epiphany. NASA's approach to Mars was fundamentally broken. Every proposal followed the same pattern. Build everything on Earth, launch it all to Mars, bring it all back. This required enormous spacecraft, multiple launches, orbital assembly, and budgets in the hundreds of billions. But what if you flipped the paradigm? What if instead of bringing everything with you, you made what you needed when you got there? This simple idea would become Mars Direct, the most influential Mars mission architecture ever conceived, and the blueprint for virtually every serious Mars plan developed since. Zubrin's breakthrough was propellant production. Mars has an atmosphere that's 95% carbon dioxide. You can react carbon dioxide with hydrogen using a simple chemical process called the Sabatier reaction to produce methane and water. The methane becomes rocket fuel. The water can be split into hydrogen and oxygen through electrolysis, giving you more rocket fuel and breathable air. The only thing you need to bring from Earth is a small amount of hydrogen to start the process, plus energy from solar panels or a nuclear reactor. Zubrin calculated that you could manufacture all the propellant needed for the return trip to Earth using just 6 tons of hydrogen brought from Mars, compared to hauling 96 tons of pre-made propellant. This single change reduced mission mass by 90% and costs by a similar amount. But Zubrin went further. Mars Direct would send cargo ahead of crew. First, you'd launch an Earth return vehicle to Mars, basically a rocket with a habitat attached, along with the equipment to manufacture propellant. The ERV would spend 26 months on Mars making fuel from the atmosphere, completely uncrewed. Once telemetry confirmed the tanks were full, you'd launch the crew in a separate habitat. They'd land near the fully fueled ERV, spend 18 months exploring Mars, then climb into the ERV and come home. If something went wrong with the ERV, the crew would never leave Earth, because you wouldn't launch them until you knew their ride home was ready. The habitat Zubrin designed was ingeniously simple. It would be a 2-story cylinder, about 8 meters in diameter and 5 meters tall, providing 100 square meters of living space for a crew of 4. The lower deck would contain life support systems, a small laboratory, an airlock, and storage. The upper deck would have crew quarters, a galley, exercise equipment, and a common area. The whole thing would weigh about 25 tons at launch and could be sent to Mars using a single heavy-lift rocket comparable to the Saturn V. No orbital assembly, no space station, no fleet of spacecraft. Just 2 launches per mission, 1 for cargo, 1 for crew, repeating every 26 months as launch windows aligned. Zubrin estimated the total cost for the first mission at $20 to $30 billion spread over 10 years, less than NASA spent on the Space Shuttle program in a single decade. For follow-up missions, costs would drop to just a few billion each, because you'd reuse the same hardware designs and production lines. Zubrin presented Mars Direct at the Case for Mars conference in Tisset, 1990, and the reaction was explosive. Here, finally, was a Mars plan that didn't sound like science fiction. It used existing technology. The Sabatier reaction had been demonstrated in labs for decades. Heavy-lift rockets could be built using shuttle-derived components. The mission profile was conservative, with multiple abort options and redundancy built in. NASA took notice, and in 1991, Zubrin was invited to present Mars Direct to the agency's leadership. They loved the elegance of the concept, but hated the implications. If Mars could be done for $30 billion, why had NASA been claiming it would cost $450 billion? The 90-day report from 1989 was suddenly revealed as embarrassingly wasteful. Worse, Mars Direct didn't require a space station, a lunar base, or any of the infrastructure NASA wanted to build. It was a direct shot to Mars, bypassing all the intermediate steps that kept NASA centers employed. So NASA did what large bureaucracies do. They took Zubrin's concept, made it more complicated and expensive, and called it the Design Reference Mission. Between 1993 and 1998, NASA published multiple versions of the DRM, each one incorporating elements of Mars Direct while adding back complexity. The crew size increased from 4 to 6. The habitat got bigger and heavier. Nuclear reactors replaced solar panels. A separate rover vehicle was added. Multiple redundant systems were specified. By the time NASA finished revising, the mission architecture looked more like the bloated proposals of the 1980s than Zubrin's elegant original. But the core concept survived. In situ propellant production, sending cargo ahead of crew, and living off Martian resources. These ideas became foundational to all subsequent Mars planning. Every NASA Mars concept since the 1990s, from the Constellation program to Artemis to current planning, assumes in situ resource utilization. Zubrin didn't get his version of Mars Direct built, but he changed how everyone thinks about Mars missions. Frustrated by NASA's bureaucratic dilution of his ideas, Zubrin co-founded the Mars Society in 1998, a non-profit advocacy organization dedicated to promoting Mars exploration and settlement. The Society's mission was to keep public pressure on NASA and Congress, conduct Mars analog research, and demonstrate the technologies needed for Mars missions. Zubrin's 1996 book, The Case for Mars, became the movement's Bible, selling hundreds of thousands of copies and inspiring a new generation of Mars enthusiasts. But we're getting ahead of ourselves. We need to talk about what NASA was actually building in the 1990s, which wasn't a Mars mission or a moon base, but a space station. The International Space Station was approved in 1993 as a compromise after the Space Exploration Initiative collapsed. It wasn't meant to be a stepping stone to colonies. It was sold to Congress as a scientific research facility, a permanent laboratory in orbit where astronauts would conduct experiments in microgravity, materials science, medicine, and basic physics. But for anyone interested in space colonization, the ISS represented something more important: proof that humans could live in space long-term. The station would become a testbed for life support systems, closed-loop resource recycling, and the psychological challenges of isolation. If we couldn't make the ISS work, we had no business attempting Mars. Construction of the ISS began in 1998 and continued for over a decade, involving 5 space agencies and contractors from 15 countries. The station grew module by module, launched on Russian Proton rockets and the Space Shuttle, assembled by astronauts in hundreds of hours of spacewalks. By 2011, the ISS was complete, a sprawling structure the size of a football field with pressurized volume equal to a 6-bedroom house, housing a permanent crew of 6. The station orbits Earth every 90 minutes at an altitude of about 400 kilometers, requiring periodic boosts to counteract atmospheric drag. Supplies arrive every few months on robotic cargo ships from the US, Russia, Europe, and Japan. Crew rotate every 6 months, launched on Russian Soyuz capsules and, more recently, American commercial crew vehicles. The ISS has taught us an enormous amount about long-duration spaceflight. We've learned that microgravity causes bone density loss of about 1% per month, muscle atrophy, vision problems from increased intracranial pressure, and immune system suppression. We've learned that radiation exposure in low Earth orbit is manageable, but would be much worse beyond Earth's magnetic field. We've learned that even highly trained astronauts experience psychological stress from confinement, isolation, and separation from family. Some crew members adapt easily to 6-month stays. Others struggle with depression and interpersonal conflicts. The station has been a laboratory for studying these problems and testing countermeasures. Exercise regimens, dietary supplements, radiation shielding, and crew support protocols. But here's what the ISS hasn't demonstrated: closed-loop life support. The station recycles some water and oxygen, but it's heavily dependent on regular resupply from Earth. Every year, dozens of tons of food, water, spare parts, and equipment are launched to keep the station operational. A Mars colony couldn't work this way. The transit time to Mars is 6 to 9 months each way, and launch windows only align every 26 months. You can't send an emergency supply run if something breaks. Mars colonies need to be self-sufficient in ways the ISS never attempted. There have been experiments on the ISS testing plant growth in microgravity, evaluating different crops, and studying closed-loop ecosystems, but these have been small-scale demonstrations, not operational systems. The ISS proved we can survive in space with constant support from Earth. It didn't prove we can thrive independently, and that's the critical difference for colonization. The other lesson from the ISS is cost. The station has cost over $150 billion to build and operate, making it the most expensive single object ever constructed. For that price, we have a laboratory that houses 6 people in low Earth orbit. Scaling this cost model to Mars is terrifying. If 6 people in orbit cost $150 billion, how much would 100 people on Mars cost? This is why many space advocates view the ISS as a cautionary tale. It demonstrated that long-duration spaceflight is possible, but at costs that make colonization seem economically absurd. The ISS became an end in itself, consuming NASA's budget for decades while producing relatively little that advances the goal of settling other worlds. Harsh, perhaps, but not entirely unfair. In 2004, President George W. Bush announced a new vision for space exploration, later formalized as the Constellation Program. The plan was to retire the Space Shuttle by 2010, finish construction of the ISS, and then return astronauts to the Moon by 2020, establishing a permanent base that would serve as a proving ground for Mars missions. This was the third time in 15 years a president had announced a return to the Moon, after Bush's father in 1989 and brief attempts during the Clinton administration. Maybe this time would be different. Bush directed NASA to develop the necessary hardware, and the agency responded with an architecture that was once again expensive and complicated. Constellation would require 2 new rockets, Ares I for crew launches and Ares V for cargo. Ares I would be a slender rocket using a single shuttle solid rocket booster as the first stage and a new upper stage burning liquid, hydrogen, and oxygen. It would launch the Orion crew capsule, a larger and more capable successor to Apollo that could carry 6 astronauts to the ISS or 4 to the Moon. Ares V would be a monster, comparable to the Saturn V, using 2 shuttle solid rocket boosters strapped to a core stage with 5 Space Shuttle main engines, topped by an upper stage. It would launch the Altair lunar lander and cargo to support surface operations. The plan was to launch Orion on Ares I and Altair on Ares V, rendezvous in orbit, and then head to the Moon. This Earth orbit rendezvous architecture was similar to Apollo but with much larger and more capable spacecraft. The Altair lander was the most ambitious part of Constellation. Unlike the Apollo lunar module, which supported 2 astronauts for 3 days, Altair would land 4 crew for 7 days initially, with upgrades allowing 14-day and eventually 180-day stays. The lander would mass about 45 tons, compared to the LM's 15 tons, and would be capable of landing anywhere on the Moon, not just equatorial sites. The design included a pressurized rover that could detach from the lander, allowing crew to drive dozens of kilometers from the landing site while remaining in shirt-sleeve comfort. NASA planned to land Altair missions at the lunar South Pole, where permanently shadowed craters were believed to contain water ice. If that ice could be mined and processed, it would provide water, oxygen, and potentially rocket propellant, enabling long-term habitation. The lunar outpost design evolved through multiple iterations. Early concepts showed inflatable habitats similar to those proposed in the 1980s. Later versions featured rigid modules connected by tunnels, looking like a smaller version of the ISS on the lunar surface. The base would be powered by solar panels during the lunar day and batteries or fuel cells during the night, or possibly by a small nuclear reactor for continuous power. Crew would live in the habitats between excursions in spacesuits or the pressurized rover, conducting geological studies, testing resource extraction equipment, and preparing for eventual Mars missions. The goal was to have a permanent crew presence by the mid-2020s, with astronauts rotating every 6 months similar to the ISS. For about 5 years, Constellation made real progress. NASA spent over $10 billion on development. The Ares I rocket completed preliminary design reviews. Test articles were built and fired. The Orion capsule was developed and tested, including a high-altitude abort test in 2010 that successfully demonstrated the launch escape system. The Altair lander reached advanced design stages with detailed Chi-D models and component testing. Hardware was being manufactured. Contracts were signed. Launch facilities at Kennedy Space Center were being modified to support the new rockets. For people who'd spent decades watching paper colonies fail to materialize, Constellation felt different. This wasn't a study. This was actual hardware development. Then, in 2009, the Augustine Commission reviewed Constellation and delivered a devastating verdict. The program was behind schedule and over budget. Ares, I wouldn't be ready until 2017 at the earliest, leaving a 6-year gap after shuttle retirement with no American crew launch capability. Ares 5 was even further behind and vastly more expensive than initially projected. The lunar landing wouldn't happen by 2020, more like 2028, and only if funding increased substantially, which wasn't going to happen. Most damning, the Commission concluded that even if Constellation succeeded in returning to the Moon, NASA's budget couldn't sustain both lunar operations and ISS support. Something had to be cut. President Obama made the decision in 2010. Constellation was canceled. The Ares rockets were scrapped. The Altair lander was terminated. Only Orion survived in modified form, to be launched on a different rocket for deep space missions. The cancellation of Constellation was brutal. NASA had spent over a decade and $10 billion with nothing to show for it except test hardware and broken contracts. Thousands of aerospace workers were laid off. The dream of a lunar base by 2020 evaporated. Critics argued that Constellation failed for the same reasons. The Space Exploration Initiative and Apollo applications failed. It was too expensive, too complex, and lacked sustained political support. The architecture required 2 new rockets when commercial alternatives or shuttle-derived options could have worked. It tried to do too much, returning to the Moon and preparing for Mars simultaneously, when focusing on one goal might have succeeded. The program became a cautionary tale about how not to design a space exploration program, which is unfortunate because technically, Constellation was sound. The engineering worked. What failed was the politics and the budget. While NASA was spending billions on canceled programs, the Mars Society was conducting actual colony simulations on shoestring budgets. In 2000, the Society established the Flashline Mars Arctic Research Station on Devon Island in the Canadian Arctic. Devon Island is the largest uninhabited island on Earth, a barren landscape of rock and ice that resembles Mars more than almost anywhere else on the planet. The research station was a small cylindrical habitat, 8 meters in diameter and 2 stories tall, housing crews of 6 for weeks at a time. The habitat was designed to simulate the constraints of a real Mars base: limited space, limited power, and complete dependence on stored supplies. Crew members wore simulated spacesuits whenever they left the habitat, conducting geological surveys, testing equipment, and studying the psychological effects of isolation. The Flashline station operated intermittently through the early 2000s, hosting dozens of crew rotations. But the Arctic location proved logistically difficult and expensive. Resupplying the station required chartering flights to one of the most remote places on Earth. Extreme weather limited the operational season to a few months per year. In 2002, the Mars Society established a second facility, the Mars Desert Research Station in southern Utah. MDRS was more accessible, located in a Mars-like desert environment near Hanksville, a town of about 200 people. The station used a similar habitat design to Flashline, housing crews of 6 for 2-week rotations. But because Utah was easier to reach, MDRS could operate year-round, hosting back-to-back missions for months at a time. Over the past 20 years, MDRS has hosted over 200 crew rotations, involving more than 1,500 participants from dozens of countries. The station became a test bed for Mars mission operations, testing everything from spacesuit designs to food production to crew dynamics. Each crew follows strict simulation protocols. They wear spacesuits during EVAs, maintain airlocks, ration water and power, and communicate with mission control using time-delayed radio as if they were actually on Mars. The data collected from these simulations has informed our understanding of what works and what doesn't in isolated, confined environments. We've learned that crews need adequate privacy. Individual sleeping quarters are essential, even though they consume valuable space. We've learned that food quality matters enormously for morale. Freeze-dried meals get monotonous quickly, and crews that cook together bond better. We've learned that conflicts often arise from trivial issues, someone leaving dishes dirty or playing music too loudly, because there's no escape from annoying crewmates. The psychological lessons from MDRS and Flashline have influenced NASA's mission planning. The agency now includes psychologists in crew selection, trains astronauts in conflict resolution, and designs habitats with more private space than earlier concepts allowed. But the Mars Society simulations also revealed limitations. Living in a small habitat in Utah for 2 weeks is nothing like spending 2 years on Mars. The MDRS crews know they can quit any time, walk outside without a spacesuit if they choose, and drive to town for supplies. The psychological stress of genuine isolation, knowing you're 200 million kilometers from help with no possibility of evacuation, cannot be simulated on Earth. Still, the Mars Society stations remain the longest-running, most realistic colony simulations ever conducted, and they continue operating today, training the people who might someday crew actual Mars missions. Before the Mars Society built their simulations, another group attempted something far more ambitious. In 1991, a team of scientists and engineers sealed 8 people inside Biosphere 2, a massive glass and steel structure in the Arizona desert designed to be a completely closed ecological system. Biosphere 2 was 3 acres of enclosed ecosystems: rainforest, ocean, savanna, desert, and agricultural zones, along with living quarters for the crew. The goal was to prove that humans could survive indefinitely in a sealed environment, recycling all air, water, and waste without any external inputs. If successful, Biosphere 2 would demonstrate that space colonies were feasible. If it failed, well, that would be informative too. The project was funded by billionaire Ed Bass, who poured $200 million into construction. The structure was enormous, containing 3.14 million cubic feet of sealed volume. The ecosystems were stocked with thousands of species of plants and animals carefully selected to create stable food webs. The agricultural zone grew crops using intensive techniques to maximize food production in limited space. The crew, 4 men and 4 women, entered Biosphere 2 in September 1991, and the hatches were sealed. They would remain inside for 2 years, growing their own food, recycling their waste, and attempting to maintain the delicate ecological balance of the miniature world they inhabited. Things started going wrong almost immediately. Oxygen levels began dropping. The plants and soil were consuming more oxygen than they produced, contrary to predictions. By 16 months into the mission, oxygen concentration had fallen from 21% to 14%, equivalent to living at 4,000 meter altitude. The crew was experiencing symptoms of hypoxia, fatigue, difficulty concentrating, and sleep disruption. The decision was made to pump oxygen into the structure, violating the closed system protocol. The reason for the oxygen loss was eventually traced to microbes in the soil, which were respiring faster than anticipated and sequestering oxygen in the form of carbon compounds. The ecological models used to design Biosphere 2 had underestimated microbial activity by an order of magnitude. Other problems cascaded. The agricultural zone couldn't produce enough food, and the crew lost an average of 13% of their body weight. Most of the vertebrate species introduced into the ecosystems died, including all of the pollinating insects, forcing crew members to hand-pollinate crops. Invasive species, particularly cockroaches and ants, overran parts of the structure. Carbon dioxide levels fluctuated wildly, sometimes spiking to dangerous concentrations. The crew split into two factions that barely spoke to each other, a situation exacerbated by the intense media attention and external management conflicts. By the time the crew emerged in September 1993, Biosphere 2 was widely considered a failure, and a second mission in 1994 with a different crew ended early after just 6 months when management disputes led to sabotage of the structure. So, what did we learn from Biosphere 2? First, closed-loop ecosystems are vastly more complicated than anyone anticipated. You can't just throw plants and animals together and expect stability. The system requires constant monitoring and intervention. Second, scaling matters. Some ecological processes that work at small scales fail at larger scales, and vice versa. Biosphere 2 was too large to manage precisely, but too small to achieve natural stability. Third, human intervention is essential. The fantasy of a self-regulating ecosystem that provides for human needs without constant management is just that, a fantasy. Modern colony designs no longer assume closed ecosystems will work. Instead, they plan for hybrid systems with significant technological components: chemical scrubbers for CO2, artificial lighting for crops, and heavy reliance on stored reserves and resupply. Biosphere 2 killed the dream of self-sufficient ecological space colonies, but it gave us realistic expectations about what's actually required. The structure still exists today, operated by the University of Arizona as a research facility studying Earth's ecosystems. It's a monument to ambitious failure and the hard lessons learned from attempting what no one had tried before. While Biosphere 2 was struggling with closed ecosystems, a different approach to space habitats was emerging from the private sector. In the late 1990s, Robert Bigelow, a billionaire who made his fortune in budget hotels, became obsessed with space stations. Bigelow believed that inflatable habitats, the same technology proposed for lunar bases in the 1960s, could revolutionize space construction. Inflatable modules would pack efficiently for launch, expand to large volumes in orbit, and provide better radiation protection than metal structures due to their multi-layered walls. In 1999, Bigelow founded Bigelow Aerospace and licensed TransHab technology from NASA. TransHab was an inflatable habitat concept NASA developed for Mars missions before Congress canceled funding. The module would have been 8 meters in diameter when inflated, providing spacious living quarters for astronauts during the long journey to Mars. NASA built and tested prototypes but never flew the design. Bigelow took the TransHab concept and ran with it. His engineers developed the BA-330, an inflatable module providing 330 cubic meters of volume, roughly 1/3 the pressurized space of the entire ISS in a single module. The module would be launched deflated atop a rocket, then inflated in orbit using onboard gas canisters. The walls consisted of multiple layers: an outer layer for micrometeorite protection, intermediate layers for structural support, and an inner layer as the pressure vessel. The design had been thoroughly analyzed and tested on the ground. Bigelow wanted to prove the concept with flight tests, so in 2006 and 2007, his company launched two subscale prototypes, Genesis 1 and Genesis 2, on Russian rockets. Both inflated successfully and remained in orbit for years, demonstrating that the technology worked. Bigelow had grander ambitions. He envisioned commercial space stations assembled from multiple BA-330 modules, leased to governments, corporations, and even wealthy tourists. The BA-330 could serve as orbital hotels, research facilities, or manufacturing plants. Because inflatables are so efficient, Bigelow claimed he could build and launch a station for a fraction of NASA's costs. He talked about lunar bases using inflatable modules buried under regolith, Mars habitats, and even bases on asteroids. The technology was sound. The company had working prototypes in orbit, and Bigelow was willing to invest hundreds of millions of his own money. For a moment, it seemed like private space stations might actually happen. NASA took notice and in 2016 contracted with Bigelow to send a smaller module, Beam, to the International Space Station as a test. Beam was launched in the trunk of a SpaceX Dragon cargo ship, attached to the ISS and inflated. It's still there today, being used for storage and occasionally for crew experiments. The module has performed flawlessly, proving that inflatable habitats work in the real space environment. But despite this success, Bigelow's broader vision never materialized. The commercial market for space stations didn't exist. Governments weren't interested in leasing private modules. Space tourism remained too expensive for a viable customer base. Bigelow Aerospace laid off most of its staff in 2020 and effectively ceased operations. The BA-330 was never built. The lunar base concepts remained computer renderings. This is the recurring tragedy of space colonization. The technology works, but the market doesn't. Bigelow proved you can build expandable habitats cheaply and efficiently. But without customers willing to pay for access, the technology has no value. NASA's vision of the ISS as a commercial hub never panned out. Private companies aren't lining up to conduct research in microgravity. The few that tried, like Made in Space, focused on niche applications with minimal revenue. Bigelow's failure, like so many before it, wasn't technical. It was economic. No one has figured out how to make space colonization profitable, and until someone does, we're stuck launching government-funded science projects that get canceled when budgets tighten. So the 1990s and 2000s saw significant progress in understanding what space colonization requires. Mars Direct showed it could be affordable. The ISS proved humans can survive long-duration spaceflight. Constellation demonstrated that political will matters more than technical capability. Mars analog stations revealed the psychological challenges. Biosphere 2 killed the fantasy of closed ecosystems. And Bigelow showed that even working technology can't succeed without a business case. These weren't wasted decades. We learned an enormous amount. But at the end of this period, in 2010, no one lived anywhere except Earth, just like in 1990, 1970, and 1950. The next decade would be different, though. Not because governments suddenly got serious about colonization, but because billionaires with rockets and messiah complexes decided they'd do it themselves. That's where things get really interesting. In 2001, a young internet millionaire named Elon Musk joined the Mars Society and started attending their conferences. He'd sold PayPal and had money to burn, and he wanted to spend it on something that mattered. Musk became obsessed with Mars colonization, not as a science project, but as an existential imperative. He believed humanity needed a backup plan, a second planet to ensure survival if something catastrophic happened on Earth. In 2002, Musk traveled to Russia hoping to buy refurbished ICBMs to launch a greenhouse to Mars as a publicity stunt to reinvigorate public interest in space. The Russians laughed at him. On the flight home, Musk did some calculations and realized he could build his own rockets cheaper than buying theirs. SpaceX was founded later that year with an explicit goal: make life multiplanetary by establishing a self-sustaining city on Mars. For the first decade, SpaceX focused on building reliable rockets and winning NASA contracts. The Falcon 1, Falcon 9, and Dragon spacecraft proved the company could compete with established aerospace giants at a fraction of the cost. But Mars was always the end game. In 2011, Musk began publicly discussing Mars mission architectures, initially focusing on Red Dragon, a modified Dragon capsule that could land on Mars carrying scientific, payloads, or cargo. Red Dragon never flew. NASA wasn't interested in funding it, but it established SpaceX's credibility as a company serious about Mars. Then, in 2016, Musk unveiled the Interplanetary Transport System at a conference in Mexico, and jaws dropped. The ITS was absurdly ambitious, a fully reusable rocket standing 122 meters tall, the largest ever designed, capable of carrying 300 tons to Mars. The spacecraft would hold 100 passengers in relative comfort for the 6-month journey. Musk showed slick animations of ITS fleets launching from Earth, refueling in orbit, traveling to Mars in formation, and landing propulsively on the surface. The presentation looked like science fiction, but Musk insisted it was engineering. The ITS concept evolved rapidly. By 2017, it had been scaled down and renamed BFR, Big Falcon Rocket, though everyone knew what the F really stood for. BFR became Starship in 2018, and the design continued changing. The current Starship architecture consists of 2 stages: Super Heavy, a booster with 33 Raptor engines, and Starship, the upper stage that's also a spacecraft capable of landing on Mars or the Moon. The full stack stands 120 meters tall and is designed to lift 100 to 150 tons to low Earth orbit when fully reusable. Starship would launch, reach orbit, and then be refueled by multiple tanker starships launched from Earth. Once fully fueled, Starship would have enough propellant to travel to Mars, land, and theoretically return if you made more propellant there using Zubrin's in situ production methods. Musk's timeline has always been wildly optimistic. In 2016, he said the first crewed Mars landing would happen by 2024. That obviously didn't happen. By 2020, he was saying 2026. As of 2024, SpaceX is saying maybe the early 2030s for crewed missions. But here's what's remarkable. Starship is actually being built. Unlike von Braun's proposals or NASA's design reference missions, Starship exists as physical hardware. SpaceX has constructed a production facility in South Texas, churning out Starship prototypes. They've conducted numerous test flights, many ending in spectacular explosions, but each failure teaching valuable lessons. In 2023 and 2024, SpaceX achieved several successful test flights reaching space, demonstrating controlled re-entry, and executing ocean splashdowns. The company is iterating faster than any space program in history, building and testing new versions every few months. But let's talk about the actual plan, because Musk's vision goes way beyond a few exploratory missions. He wants to build a city on Mars with 1 million people by 2050. Yes, 1 million. This isn't a typo or hyperbole. Musk has repeatedly stated this goal in interviews, presentations, and on social media. The plan is to use Starship to send massive amounts of cargo to Mars, hundreds of flights per launch window, building up infrastructure before any humans arrive. Robots and automated systems would construct habitats, power, plants, propellant production facilities, and life support systems. Once the basic infrastructure is in place, humans would start arriving, initially in small numbers, then ramping up to thousands per launch window. The economics, according to Musk, work because Starship will be fully reusable, dropping launch costs to a few $1,000,000 per flight. If you can get the cost per ton to Mars down to around $100,000, transporting 1 million people becomes theoretically affordable, though we're still talking about trillions of dollars total. There are so many problems with this plan, it's hard to know where to start. First, full reusability hasn't been demonstrated yet. Starship might achieve it. The engineering looks sound, but it's not proven. Second, even if launch costs drop as predicted, building a city on Mars requires more than just transportation. You need habitats that can withstand the environment, life support systems that work reliably for years, food production at massive scale, energy generation, mining and manufacturing, and a closed-loop economy. None of this exists even in prototype form. Third, there's the radiation problem. Mars has no magnetic field and a thin atmosphere, meaning surface radiation exposure is about 1,000 times higher than Earth. You can't just walk around on Mars. You'd need underground habitats or extensive shielding, adding enormous mass and cost. Fourth, the physiological effects of Martian gravity, 38% of Earth's, are completely unknown. Maybe humans adapt fine. Maybe they don't. We won't know until people actually live there for extended periods. The timeline is, frankly, absurd. Musk says 1 million people by 2050, which is 26 years away as I'm recording this. Let's be generous and say crewed missions start by 2035. That leaves 15 years to transport 1 million people. Launch windows to Mars occur every 26 months, so that's about 7 launch opportunities. You'd need to send roughly 140,000 people per launch window. If each Starship carries 100 people, that's 400 Starship flights per window, or about 10,000 total flights. SpaceX would need to launch multiple Starships per day, every day, for months during each launch window, maintain this pace for 15 years, and do it all while simultaneously building the infrastructure to support 1 million people on Mars. It's not going to happen. Not by 2050, probably not by 2100. But here's the thing. It doesn't matter if Musk's timeline is fantasy. What matters is that SpaceX is actually building the hardware that could enable Mars colonization, even if on a much smaller and slower scale than advertised. If Starship works and costs really do drop, then Mars missions become feasible in a way they never were before. The first crewed landing might not happen until 2040. The first base might house dozens, not millions. But it would be a start, which is more than we've had in 50 years. While SpaceX pursues Mars, NASA has returned to the Moon. In 2017, the Trump administration directed NASA to focus on lunar exploration, leading to the Artemis program. Artemis is supposed to land the first woman and first person of color on the Moon, establish a permanent base called Artemis Base Camp at the lunar South Pole, and use the Moon as a proving ground for Mars technologies. The program architecture is complicated, involving multiple international partners, commercial contractors, and a small space station in lunar orbit called Gateway. Gateway is essentially a miniature ISS orbiting the Moon, serving as a staging point for lunar landings. It consists of several modules providing living space, docking ports, and storage. The station is being built by NASA, ESA, JAXA, and CSA, with modules launching on commercial rockets starting in the mid-2020s. For lunar landings, NASA selected SpaceX's Starship as the primary lander under a contract worth billions. Yes, the same Starship intended for Mars will first land astronauts on the Moon. Starship will launch to Earth orbit, refuel from tanker starships, travel to lunar orbit, dock with Gateway to pick up astronauts, land on the Moon, stay for about a week, return to Gateway, and then the crew flies home on Orion. This architecture is Baroque, involving multiple launches, orbital refueling, and complex choreography. But it allows NASA to use the SLS rocket and Orion capsule, preserving jobs at legacy contractors while leveraging SpaceX's cheaper Starship for the actual landing. The first crewed landing is currently scheduled for 2027, though most observers expect delays pushing it to 2028 or later. Artemis Base Camp is the long-term goal. The base would be located at the lunar South Pole, near permanently shadowed craters containing water ice. Initial missions would last a week, gradually extending to month-long stays as infrastructure is built up. The base design includes a small pressurized habitat for 4 astronauts, an unpressurized rover for exploration, a pressurized rover for long-distance traverses, and equipment for excavating and processing ice. Power would come from solar panels positioned to catch sunlight on crater rims or from small nuclear reactors. The base wouldn't be permanently occupied initially. Crews would come and go, spending a few weeks or months at a time. Permanent occupation might begin in the 2030s if funding continues. NASA describes Artemis as sustainable, meaning it's supposed to be affordable over the long term, unlike Apollo, which became unsustainable and was canceled. But sustainable keeps getting redefined as costs escalate. The elephant in the room is the Space Launch System, NASA's heavy-lift rocket for Artemis. SLS is a shuttle-derived design using shuttle main engines, solid rocket boosters, and a core stage with a design lineage going back decades. It's powerful, capable of lifting 27 tons to lunar orbit initially and 40 tons in upgraded versions. It's also obscenely expensive. Each SLS launch costs over $4 billion once development costs are amortized, and even marginal costs per launch are close to $2 billion. For comparison, SpaceX's Falcon Heavy can launch for under $200 million, and Starship is projected to cost just a few million per launch when operational. NASA is stuck with SLS because Congress mandates its use to preserve jobs in key districts. The rocket works fine. Technically, it's very capable, but it's economically insane. Artemis would be far cheaper using commercial launchers, but politics trumps economics. The realistic timeline for Artemis is uncertain. The first crewed landing might happen by the late 2020s. The base could be established in the 2030s if funding remains stable. But there's enormous pressure to cancel Artemis, just like Constellation was canceled, because the costs keep climbing and the program lacks public support. Recent polls show most Americans don't think returning to the Moon is worth the cost. Congress debates cutting NASA's budget every year. Unless Artemis delivers something compelling soon, it's vulnerable to cancellation. the one thing working in its favor is international partnerships. ESA, JAXA, and CSA have invested in gateway and lunar infrastructure, making cancellation politically complicated. But if SpaceX lands Starship on the Moon successfully for a fraction of NASA's costs, it will raise uncomfortable questions about why we need SLS and Artemis at all. While NASA plans and SpaceX builds, China has been quietly executing its own lunar program. China landed its first rover on the Moon in 2013, returned samples in 2020, and landed a rover on the far side in 2019, a first for any nation. The country is now developing crewed lunar capabilities with a target of landing astronauts, or taikonauts in Chinese terminology, by the mid-2030s. China's approach is methodical and well-funded. Unlike NASA's frequent program cancellations and direction changes, China's space program benefits from long-term planning and consistent funding, insulated from political cycles. The Chinese lunar architecture involves the Long March 10 rocket, currently in development, which will launch crewed missions using a new spacecraft and lunar lander. The plan is to establish an international lunar research station in partnership with Russia, though Russia's contribution is uncertain given their economic situation. The ILRS would be located at the lunar South Pole, similar to Artemis Base Camp, and would begin with robotic infrastructure delivered by uncrewed missions in the late 2020s. Chinese astronauts would arrive in the early to mid-2030s, conducting extended stays to explore, test technologies, and begin resource utilization. China has explicitly stated the goal is permanent habitation, not flags and footprints visits. What's notable about China's plan is the lack of bombastic timelines and grandiose promises. Chinese officials speak cautiously about schedules and capabilities, in stark contrast to Musk's million-person Mars, SITI, or NASA's constantly revised Artemis timelines. This measured approach, combined with China's track record of meeting stated goals, suggests they might actually succeed. There's a real possibility that by 2040, China will have a functioning lunar base while NASA is still debating sustainable architectures and SpaceX is focused on Mars. For Americans accustomed to space dominance, this is uncomfortable. But from a pure capability standpoint, China is executing a credible lunar colonization plan. The geopolitical implications are significant. If China establishes the first permanent off-world human presence, it shifts the narrative of space exploration. It's no longer American-led with international partners. It becomes multipolar with China as a major player. This might actually be good for space colonization. Competition historically drives faster progress than cooperation. The space race of the 1960s achieved more in a decade than the international cooperation era has in half a century. If China's lunar base spurs the United States to accelerate its own plans, we all benefit. But it could also lead to territorial disputes, competing claims, and a lack of coordination that makes future colonization more dangerous and inefficient. Then there's Jeff Bezos and Blue Origin. Bezos founded Blue Origin in 2000, 2 years before Musk started SpaceX, with a vision even grander than Mars colonization. Bezos wants millions of people living and working in space, not on planets but in O'Neill cylinders orbiting Earth. He's a true believer in Gerard O'Neill's vision from the 1970s and argues that Mars is the wrong destination. Planets have gravity wells, limited surface area, and environmental constraints. Space colonies have none of these problems. You can build as many as you want, customize their environments, position them near resources, and expand indefinitely. Bezos's ultimate vision is trillions of humans living in orbital habitats, with Earth preserved as a beautiful nature reserve while heavy industry moves to space. This is a lovely vision, but Blue Origin's progress has been glacial compared to SpaceX. The company spent 2 decades developing New Shepard, a suborbital rocket for space tourism that finally began commercial flights in 2018. New Glenn, Blue Origin's orbital rocket comparable to Falcon Heavy, has been in development for over a decade and still hasn't flown as of late 2024. Blue Origin did win a NASA contract to develop a lunar lander called Blue Moon, which would deliver cargo and eventually astronauts to the lunar surface as part of Artemis. Blue Moon uses a more traditional architecture than Starship, with separate ascent and descent stages, and would launch on New Glenn. But development has been slow, and the first uncrewed landing isn't expected until the late 2020s at the earliest. Bezos also partnered with Sierra Space to develop Orbital Reef, a commercial space station intended to replace the ISS after it's retired in the 2030s. Orbital Reef would provide laboratory space, manufacturing facilities, and accommodations for tourists and researchers. It's a reasonable concept, and NASA has provided some funding, but progress is minimal. Blue Origin announced Orbital Reef in 2021 with a projected operational date of 2027. That's obviously not happening. The project seems perpetually in early development with no hardware flying. The fundamental problem with Blue Origin is pace. The company has Bezos's billions, talented engineers, and solid technology, but it moves cautiously, testing exhaustively and avoiding the rapid iteration approach SpaceX uses. This might produce more reliable hardware eventually, but it means Blue Origin is always years behind. By the time New Glenn finally flies, Falcon Heavy will have been operational for nearly a decade. By the time Blue Moon lands on the Moon, SpaceX's Starship will likely have done so multiple times. Bezos talks about the long game, building infrastructure over decades, and he's probably right that this is how you get to O'Neill cylinders and millions of people in space. But in the near term, Blue Origin's slow pace means it's not driving the colonization conversation the way SpaceX is. Before we assess timelines, we need to talk about Mars sample return, because it might determine whether Mars colonization is even possible. MSR is a joint NASA-ESA mission to bring Martian rocks and soil back to Earth for detailed analysis. The mission is critical for several reasons. First, we need to know if Mars ever harbored life, and the only way to definitively answer that is laboratory analysis of samples with equipment too large to send to Mars. Second, we need to understand Martian geology, soil chemistry, and resource availability to plan colonies. Third, and most important, we need to ensure Mars doesn't harbor organisms that could be dangerous to Earth life. This sounds like science fiction, but it's a real concern called planetary protection. The mission architecture involves 3 spacecraft. First, a rover collects samples and places them in sealed containers on the Martian surface. Second, a lander retrieves the containers, launches them into Mars orbit using a small rocket, and a third spacecraft captures them and returns to Earth. The samples would arrive in the early 2030s and be analyzed in a specially designed containment facility. If the samples show evidence of past or present life, it changes everything. If Martian microbes exist, we need to understand whether they're compatible with Earth biochemistry, whether they pose a contamination risk, and whether humans can safely live on Mars without being exposed to potentially harmful organisms. Mars sample return has been in planning for decades, but it's now facing a budget crisis. The mission was originally costed at $3 billion. Current estimates are approaching $10 billion, and NASA doesn't have that money. The mission has been delayed multiple times and might be canceled entirely or drastically redesigned to cut costs. This is incredibly frustrating because MSR is arguably the most important precursor to human Mars missions. You don't send people to a planet without knowing if it's biologically safe. If MSR gets canceled, it pushes back Mars colonization timelines by decades because we'd need alternative ways to answer these questions. Let's talk about the failures, because for every SpaceX making progress, there are a dozen ventures that announce grand plans and then disappear. Mars One was the most infamous. In 2012, a Dutch nonprofit announced plans to establish a permanent Mars colony funded by a reality TV show. They'd send people on one-way missions starting in 2023, broadcasting the selection process, training, and eventual Mars landing. The whole thing was a scam. Mars One had no technology, no funding beyond a few $100,000 from merchandise sales, and no realistic plan. The founder, Bas Lansdorp, claimed they'd raise billions from TV rights, but no broadcaster ever signed on. Aerospace engineers analyzed the plan and found it wildly implausible. By 2019, Mars One declared bankruptcy, having accomplished nothing except collecting application fees from tens of thousands of people who wanted to go to Mars. Inspiration Mars was more legitimate, but equally unsuccessful. In 2013, Dennis Tito, the first space tourist, announced plans to send a married couple on a Mars flyby in 2018. The mission would use a free return trajectory, looping around Mars without landing and returning to Earth. Total duration 501 days. Tito pledged $100 million of his own money and expected NASA to contribute the rest. NASA declined, and without government support, Tito couldn't raise the necessary billions. The mission was quietly abandoned by 2015. Tito tried reviving it in 2018 with different architectures, but again failed to secure funding. The pattern is clear: announcement, media attention, failure to secure funding, quiet cancellation. This has happened repeatedly. Most recently, several companies announced lunar base plans, cargo delivery services, and Mars missions, only to fold or pivot after burning through investor money. The problem is that space colonization requires sustained commitment of tens or hundreds of billions of dollars, and very few entities have both the resources and the will to make that commitment. Governments have the resources but not the will. Billionaires have the will but not quite enough resources. And private companies need a business case that doesn't exist yet. So let's synthesize all of this into a realistic timeline. Can we actually colonize the solar system, and if so, when? Here's my best assessment based on current technology, funding, and political realities. The Moon might see a permanent base by the late 2030s or early 2040s. This assumes Artemis survives political headwinds, China follows through on its plans, or SpaceX decides a lunar base is a useful stepping stone to Mars. The base will be small, fewer than a dozen people, rotating every few months. It won't be a city or a colony in the traditional sense, more like Antarctica research stations. Permanent occupation, meaning people living there year-round for years at a time, might happen in the 2040s or 2050s if resource utilization proves economically valuable. That's a big if. Mars landing, crewed, could happen as early as the late 2030s if SpaceX succeeds with Starship and Musk remains committed. More likely is the 2040s. NASA might beat SpaceX if international partnerships hold together and funding continues. but I wouldn't bet on it. The first Mars missions will be short, a few weeks on the surface, similar to Apollo. Building up to a permanent presence will take decades. A small base with rotating crews of a dozen people might be established by the 2060s. A self-sustaining colony, meaning it could survive without resupply from Earth, probably not until the 2080s or later. Musk's million-person city, not this century, maybe not ever. The technical barriers are solvable. We know how to get to Mars, land, and return. We know how to generate power, produce propellant, and grow food in controlled environments. The engineering is hard, but not impossible. The economic barriers are more difficult. No one has articulated a compelling business case for Mars colonization. Scientific research doesn't justify the cost. Resource extraction might, but we don't know what resources Mars has that are valuable enough to export. Planetary backup doesn't resonate with the public or politicians. Without a clear economic or political driver, funding will always be precarious, and programs will be canceled. The political barriers might be insurmountable. Space exploration is expensive and has no constituency. The public is largely indifferent. Every few years, polls show most people don't think human spaceflight is worth the cost. Politicians fund NASA for jobs in their districts, not because they believe in colonization. This has been true for 50 years and shows no signs of changing. Billionaires might bypass political barriers by self-funding, but even Musk and Bezos don't have enough money to colonize planets alone. They need government contracts, regulatory approval, and infrastructure support. Then there's the looming question of climate change. Earth is facing an existential crisis that will cost trillions to address. As temperatures rise, sea levels increase, and extreme weather becomes more common. The political will to spend billions on space colonies will evaporate. Why colonize Mars when we need to save Earth? The counter-argument is that the same technologies needed for Mars colonization, closed-loop life support, renewable energy, resource efficiency, could help on Earth. There's some truth to this, but it's a hard sell when people are losing homes to floods and wildfires. Climate change might kill space colonization by consuming all available resources and attention. So, is colonization inevitable human destiny, or are we trapped in our cradle forever? I honestly don't know. We've been planning to leave Earth for over 150 years. Every generation has believed they'd be the ones to finally do it. The dreamers of the 1860s thought moon colonies would exist by 1950. The engineers of the 1950s thought we'd have lunar bases by 1980. The advocates of the 1980s thought Mars would be settled by 2020. Every prediction has been wrong. Every timeline has slipped. Every grand plan has been canceled or scaled back. Yet here we are, still planning, still designing, still believing the next proposal will be the one that works. Maybe that's the point. Maybe space colonization isn't about the destination, but the pursuit. The planning itself drives technological progress. Rockets get better. Life support systems improve. Our understanding of other worlds deepens. Even failed programs like Constellation advance to the state of the art. Even canceled missions like Mars Sample Return teach us what doesn't work. We're building up institutional knowledge, engineering capability, and eventually, maybe, we'll reach a tipping point where colonization becomes not just possible but inevitable. Or maybe we're fooling ourselves. Maybe we're a planet-bound species destined to remain on Earth, sending robots to explore on our behalf while we watch from home. Maybe the economic and political barriers are genuinely insurmountable. and space colonization will remain forever just beyond our grasp. A dream that inspires but never materializes. Maybe future generations will look back at our plans the way we look at Victorian schemes to build cities under glass domes, charming but impossibly naive. I'd like to believe colonization will happen. The alternative, that humanity's entire future is confined to one planet, seems unbearably limiting. But belief isn't analysis, and honest analysis suggests that while small outposts might be established in the coming decades, true colonization, thousands or millions of people living permanently off Earth, remains a distant and uncertain prospect. We keep planning because we can't help ourselves. We're a species that dreams, and space colonization is the ultimate dream. Whether we're dreaming of homes we'll eventually build or homes we'll never reach, only time will tell. For now, all we can do is keep designing, keep testing, keep pushing the boundaries of what's possible, and hope that someday, finally, one of these plans will actually work.